Okay, so we're gonna do part of a quest today, and then for the daily homework 3, you're gonna do the rest of the quest.
Like, how do you do parts and things?
I can't wait to find this. It's a quest. So we're looking at spectral. Okay, and what question do we ask in spectral relativity?
There's what one frame C.
Okay, so we have one frame here. What is that frame not doing?
Not moving.
Moving, and so we just call this cessation. And there would be really an X, Y, Z here, but it's too hard to draw, so I'm just doing the X and the Y. This is X and this is Y. And then we have a
Moving frame.
moving frame. And we call these coordinates,
S per line.
we put primes on everything. And it's moving with a constant velocity v. And then we have an event. An event is anything that you can specify with a
Place in time.
place and time. So I'm not like asterisks here, so this has an X, Y, T according to S. And then it has an X prime, a Y prime, and a T prime according to S prime. So the question of how are those two related? Now the claim is going to be, the claim is that what we're going to find out is that X prime equals gamma X minus VT, Y prime equals Y, and T prime equals gamma T minus V X over C squared. And these, what do we call these equations?
Lorentz.
The Lorentz equations. Okay, and what's our buddy gamma given by?
1 over the square root of 1 minus V over C squared.
C squared. In case I forget to give it to you, V over C, we give another name to as well. Remember what that is from physics 125?
The square root of mu.
Beta. Okay.
Yes. I was over.
It's going to be a friend beta. So this is sometimes written as 1 over the square root of 1 minus beta squared. Okay, and that's what we want to show. And so again, by the meaning these coordinates just make certain we understand it. This person is going to measure everything from here, so this would be X here. Whereas this person is going to measure everything from here, this is going to be X from here. Okay. And then the same with Y and the same with Y prime. And so what did we assume? Since I went a 1-to-1 correspondence between what's measured here and here, we assume what kind of coordinates? Transformation wise? A linear transformation. And so it's going to have the variables, right? And so we started off with we assume. So this would be plus 10,000. I remember that now. Coincided with fun. Yes, plus 10,000. So we have this X prime equals A1X plus A2Y plus A3 T plus 84, and then we do the same thing for the Y from in the again, it'd be the same thing for the Z, but then it's just more quest, and it's the same idea. It's not any more quest. That should be a 2. Now, why do I have the D here instead of C? Because it turns out C follows A and B.
There's another.
Frequently called
D2.
This beautiful.
Yeah, we don't want to confuse with this. The reason we're not having C's is because to have C and then C1, C2, C3, C4, it's just too complicated. So we're going to opt to D. Let's D2Y, let's D3T, let's D4. Okay, and all we're going to do with this is basically is the quest. We're just start calculating the constants. Okay, how did we get rid of A4, B4, and D4?
By the frame having the same origin at T equals 0.
Yeah, we're going to say initially those two frames coincide. So we could say that at T prime equals T equals 0, the origins of S and S prime coincide. So A4 equals B4 equals D4 equals 0. So that gives us, we're now down to 9 coordinates instead of now 12. Okay. And then we set up the velocity equations. So the velocity equations, we said that x dot I equals dx prime over dx over dt prime equals, and then we took the differential of these things, which was forced to erase, but I did not because I wasn't forced to erase because they're there. Good. Okay, so this is a1 dx plus a2 dy plus a3 dt. And then we divide through this by the t prime, which is d1 dx plus d2 dy plus d3 dt. And then what do we do?
Multiply by 1.
In a clever fashion, which was
1 over dt over 1 over dt.
correct. And we did that. That gave us this fellow here. Okay. And then likewise for the y, you're just going to do the same thing, but with b's on top. After that, then I think we did one more thing last time. What did we do? We applied this to. I think we did.
No, did
Is this where it stopped?
think so.
Yeah. Now I have one more thing.
I thought we did the origins.
Yes.
Okay, so let's look at the origins. So let's apply this to the origins as viewed by S and S prime. Okay, does everyone have this equivalent v equals 0? Okay. That's crucial. That's what I thought. A lot of people don't understand this. Because that's just they fail.
Whatever.
Awful. So I didn't pass the death amongst physicists, not
Yeah.
realizing that the equivalent v equals 0. End up, dying.
Solve the main equation.
It was awful. Okay, so let's do this. So here we are in S. Here we are. And here's my buddy S prime. This is V. So what does S see? So in other words, we're going to look at the origin here. Okay. So if you live there, if this is a picture here, so this is the point we're looking at. So if you lived here, what would you say the velocity of your origin is? Now, if you're here, you don't think you're moving, right? So this is going to be 0. So this is 0 equals. Then we get A1. What is X dot then? What does this person see?
V.
Now they're going to see this point with a V, so this is V. And then we plus get A2, and then what is Y dot?
0.
Yeah, let's start because it's just moving this way. So this is 0. This is A3 equals D1V plus D2 0 plus D3. All right. So I take all this over to the other side, and this gives me 0 equals A1V plus A3, or this gives me, this is going to become very questy. So this will give me A3 equals minus A1V. And since I don't want to lose that, I'm going to put this over here. And the phantoms for general, so I cannot see it. Ah, you can only see part of it. Okay, questions with that? Okay, now let's do the same thing then for the y. What does y give me? So if you live in S prime, what is your y dot, the origin?
Y. 0.
Yeah, if you live here, you don't see this moving at all. So this is 0. Equals B1. What is x dot? Yeah. According to this person, x dot is still B. This is B. And plus B2 0. Plus B3. And this is all divided by D1 V plus D2 0 plus D3. So does this give me 0 equals B1V plus B3? The B3 is minus B1V. And so now this goes over here. Does that make sense? Now we're going to repeat it, but going the other way. What we're going to do, we're going to look at this origin over here. So repeat. I was forced to erase an equation. Okay, well, remember the equation. So repeat. For what? As prime C's. Okay. So if you live here, now we're going to look at this origin here. What do you see?
The origin moving away at minus V.
This is minus V. So we're going to have, for the next equation, with minus V equals what? A1. Now what is your x?
X.
Look here. What is x? What is x dot?
Minus V. No, no, 0, 0, 0.
0. That makes sense?
You.
Remember, what I'm doing here is forced to erase the superluminal block where it starts to six. And then it's this, the D thing. Okay. Well, so this one, if you're, this person is now looking at this origin. This person sees this origin going this way at minus V. But if you live here, what do you think the origin is doing? I'm moving it all so you get 0 here. That's a setting 0. Okay. Given how we that was maybe 1.
Yeah.
Oh, okay. There's a very thin, there's a fasting 0, which makes it looks like 1. Okay, so this is in what is y dot then?
0.
0. And then this is A3. And then this is what? This is D1 over
0.
0. Plus
T2 over T2 times 0.
D2 from 0 plus
T3.
D3. This gives me minus VD3 equals A3. Now we're going to put that one over here. Okay. That makes sense. Okay, now we still then have the y equation given. So what does the y equation give me?
Well, essentially the same thing.
Not quite.
Not quite.
I was going to give us something here. Over here. You're here.
Mhm.
What are you saying is the y dot prime for that coordinate.
0.
0. So you're gonna get 0 equals, and you're gonna get B1. What is x dot?
Minus B.
0, right? If you live here, you don't see that word, you move.
Oh, okay.
Plus B2 is, y dot is
0.
0. Plus B3. All over D1 times
0.
0. D2 times
0.
plus D3. Okay, what does that one give us?
0.
Not quite.
Uh,
Okay, 0 equals B3. Now we get B3 equals 0. So let's rewrite all these equations here and see what we have now. Okay, so what do we have? I'm just going to copy these equations over here. So this is A3 equals minus A1 minus 1 minus A1B. B3 equals minus BB1. A3 equals minus V minus D3, and then B3 equals 0. Okay, so what does that mean about B1?
B equals 0.
Yeah, so put this in here, so B3 equals 0 minus B1. This means that B1 equals 0. Okay, so boom. Boom. Okay. Now what happens if I take these two? This tells me that A3 is minus VD3. But A3 is also minus VA1. So this tells me that D3 is also A1. Does that make sense? Questions on that? Okay, so that said, I'm going to be writing our expressions. So what do we have now? Now we have x, so the Lorentz transformation equations. X prime equals A1 x plus B2y plus A3, and A3 is A3. Is this guy minus A1VT, like that, which I can rewrite as A1 x minus VT plus B2y. Okay, so that's my new x equation. A lot easier. What does my y prime equation now become?
Y equal Y.
Not yet. The B1 equation is the B1 constant is 0. That's how the B2 equation to the B2 constant, that's right. And that's what that equation is. Right. Now what do we have? T prime. The T prime is going to be my buddy D1. No, I don't know. There it is. D1x plus D2y. What is my buddy D3 equal to?
A1.
A1. This is A1T. Okay. These are not my new versions. So now we're down to 1, 2, 3, 4 constants. Okay. We're at 12, we're now down to 4. The quest continues. Okay. The next one's weird. I mean, I want to show you that the B2 has to be 1. And that's actually that's the hardest one to actually show in my opinion. I just want to show you that the B2 has to be 1. So consider a rod. Stationary. In S code. Line. Along. The y-axis. Okay, yell at me here.
A2.
Yeah, can this be B2 here? Absolutely not. I have no idea why I wrote that. Okay. Fix your notes and tell me when you're done.
It's stationary in y, or lying along the y-axis.
It's just the y prime axis. Okay. So we want to fix where I screwed up.
Yeah.
So let's actually draw this picture up here. So this is S. X and Y, here you are. We have this is Y prime. X prime, this is moving with velocity B. Here we are moving like that, and here's our rod like that. Okay. And this rod is going to have a length L naught according to S prime. Okay. What would this person here see? Okay, so Y prime would be what? Would be L naught. This would be B2. And then what would this person measure? I don't know. Let's just call it L. So this is the value of the Y value of the length of rod according to this. Does that make sense? I need these equations, so I will put these over here and in fact, now let's repeat the same thing. We're going to take the same rod and length L naught and put it and it's going to be stationary in S along the line axis, along the y-axis. So take the same rod of length L naught and have it at rest in S line along the y-axis. We're going to do the exact same experiment, but just on the other frame. Okay. So this person is going to measure, and we're going to apply this equation. This person is going to measure that rod here, and I'm going to call that L prime. So this value here, this is the value of the Y prime length of rod according to S prime. Equals, so what does this S equal? V2 times? No. Okay, now we're going to look at a ratio here. This is where it's a little on the sides. So let's look at the ratio of the moving value of y compared to the stationary rate. And that's, I've kind of worded this awkwardly, so we're gonna do that in each of these cases here. So in the first case. I need room. In the first case, this person sees the rod moving. All right? So what does this person say the length of the rod is?
B2L.
They just call it L.
Mm.
So this person, in the first case, S says, what do we have? We're gonna have L. This is the moving value. Waiting S. And then the stationary value is gonna be this right here, this on. Okay. Now let's go over here. In the second case, S prime says, is S prime is going to measure the moving one. What does this person say?
The rod's moving away to me.
What did they measure the length to be?
L prime.
L prime. And this is the moving value according to S prime. What's the stationary value?
Oh my.
Yeah.
Oh no. Okay. Okay. Now, what do those ratios have to be? How do they have to compare to each other and why? Tell me why they have to be the same. What would happen if they were different?
Wouldn't be a linear.
What could you then do? You could do an experiment to determine who's moving. And you can't do an experiment to determine who's moving. Right? The second postulate of relativity. It's impossible to do an experiment to determine which one's moving. If they're different, you can then do an experiment. Okay, so they have to be the same. So from the second postulate the special relativity, the ratios must be the same. So L over L naught is equal to what? Well, L over L naught is 1 over B prime, is 1 over B. Whatever. Right? And this has to equal this L prime over L naught. This guy, well, prime over L naught is B2. So this tells me that B2 squared equals, doesn't equal that now. B2 squared equals 1. In other words, B2 has to be 1. Okay, so now we have one of them done. Nothing happens, the direction is perpendicular to the motion. Does that make sense? That's a very subtle argument. That's the hardest one. Question? Okay, now let's kill A2. Okay. Now consider a rod at rest in S line S prime at rest in S line along the y-axis. As shown below. the y-axis like this. I'm gonna put that rod so it's like this. This point up here, this is gonna be the top, this is gonna be L naught over 2. And this down here is gonna be the bottom, this is L naught over 2. Here's my y, and here's my x. So basically, I'm just putting it so that half is on top, half is. Okay. And here's my x prime, y prime. This will be. Okay. Multiplier equations. Let's see, what is x? What is x prime at the top? So what would this person say is its top over here? So this is my x at the top. I'm sorry. This is y at the top here. This is y at the bottom. So what would this person say, according to this equation, is x at the top? X is
0.
it's 0. Okay, I'd like to do this experiment at a really convenient time. When do you think would a very convenient time to do this experiment would be? When t is 0. So we're also going to let t equals 0 plus a2. Now what is y at the top? On the picture.
And half building.
1 over 2. Now let's look at the bottom. So this would be what? This would be a1. What is x at the bottom?
0.
Because it's along the y-axis. It's on the x equals 0 line. 0 plus a2. Now, what is y at the bottom?
Minus L over 2.
Minus L naught over 2. If I were to say now graph this here, this is x prime, this is y prime, what would that person see? If this is the top, and if this is the bottom, what would that person see? The top would have to be over here. This would have to be our A2 over 2, so that would have to be our top value. Right? Our bottom value would be over here. So that rod is going to look something like this. Does that make sense? If this is the metric here. Yeah. Did you have this thing going like that? No, you can have it by symmetry. And also be aware of symmetry motions. So what would you have to have? The A2 value must be
0.
so therefore A2 has to equal 0. Can't have. Okay. And also what we have. Our equations now simplify quite a bit. So now we have, now I have x prime equals a1 x minus vt, y prime equals y, and our t prime equals d1x is d2y is a3t. I'm sorry, a1t. Okay, does that make sense? Now we want to kill D2. So we're going to do pretty much the same thing, but instead of having a stick, basically at, where the top is at 1 L naught over 2, and then the bottom is at minus L naught over 2, we're going to have bombs. We're going to explode the bombs at the same time. So consider. Two bounds. At rest. In S. Along. The Y. Axis. At T equals 0. At T equals 0. Both bounds explode at the same time. Yes. So let's draw this out. So here's my first bound. Let's say that this is going to be some, I'll call this L naught over 2. That. There's another bound. I'll put this one here. It's an identical bound. This is minus L naught over 2. This makes this equal 0. Let's see what this person says. So let's look at the top bound. What does this person say for the top bound?
0x.
Okay, so this would have to be D1 0 plus
V2 L log 2
over 2 plus
0.
0 because we're taking T equal to 0. Now, if you look at the bottom bound,
V not 0.
0 here,
V2 minus L log 2.
plus 0. So what do we have here? What should this person see? If these are symmetric here, they're exploding at the same time. What would this person, if this person is at the origin here, what would they have to see? Those bounds would also have to be
Like boom at the side.
simultaneous, right? So S prime must measure the explosions at the same time. So therefore,
V2 0.
need to. So now what are our final equations? And this is where I leave you with daily homework 3. So we now have x prime equals a1 x minus 3t. Y prime equals y. T prime equals d1x plus a1t. And in daily homework 1, we'll call 3. You will determine A1 and B1 and C that A1 equals gamma. Gamma is 1 over the square root of 1 times v squared plus c squared. And D1 equals minus V8 equals minus V gamma. In other words, what we're going to be left with it should be a C over there, so. And that's what. That's fine. This should be overseas, yeah.
And a V squared?
Well,
Oh, my bad.
okay. The way you're gonna do this is what haven't we used from the postulates of relativity?
That the speed of light is constant on
The speed of light is the same for
all.
all observers. So you're gonna do two cases here. So you will show, so you will make use of the speed of light. Being safe for all observers. Okay. What you're gonna do in one case, so in case one. This person's gonna have a laser and fire the laser this way. That laser is gonna travel at
Yeah.
C. So what would you say then is X dot prime, Y dot prime, X dot, and Y dot?
C0, C0.
It's just going the X direction, so this is 0, and this is 0. And this has to be C, and this has to be C. When you do that, that's gonna give you a law. And that's the first case. And then the second case. This person's gonna have the laser going like that. So what is it gonna be over here?
0C, 0C.
This has to be 0, C. Now, what will happen over here? We're gonna have to work out this one, it's gonna be weird. We're gonna have to work out this one here, and this will not be, this is not gonna equal 0. So you're gonna have the X component of the velocity of light, the Y component of the velocity of light. What are you gonna have to do with those? What would this person over here, besides having a very serious head, a head accident, have to say about light?
It's coming at an angle.
Sure, if you're gonna measure at an angle,
The total speed is still C.
and what will they say is the total C? If you have these things.
X dot squared plus Y dot squared.
X dot prime squared plus Y dot prime squared has to equal C
C
squared. Okay. And Shazam, you'll be done.
That was the point that I was missing.
Okay. That makes sense?
Yeah.
Again, not hard, but it's very questy. It's definitely questy. Okay. Now what can we do with these? Not a damn thing. No. So we can do a lot, we can do a lot. So first of all, if somebody gives you a brand new shiny theory. What had your brand new shiny theory better do?
Work.
Well, I have an old theory that's great. Works fine. It just doesn't work in a case where this my velocity is getting large. Other, but somebody that comes along with a brand new shiny theory that says it works. And what that brand new shiny theory better do?
That'd be easier to deal with.
Real small to the old problem.
And better reduce to the old equations where the old equations is valid. Okay, so. And this is true for any theory. Okay, so in other words, if somebody has, string theory, whatever they think the theory of everything is, that better reduce to classical mechanics where classical mechanics is valid. So how should it reduce to Newtonian physics? It better reduce to Newtonian physics, and they'll limit that.
E is much less than C.
The velocity has to be much less than c. Okay, so that's going to be non-relativistic. And then what we have to do, we're not gonna be on really, really small length scales, we're gonna have to be on larger length scales. And then one other thing has to go to zero. The relativity by saying B is much less than C. How do you kill quantum mechanics?
Well, H.
H has to go to zero. If I take the limit that H goes to zero and my velocity goes to zero, and if I'm dealing with bigger, length scales, then I don't have to worry about quantum gravity stuff. I better get Newton's equations. Okay, and if you don't, then it's wrong. Now they'll say, you'll ask them to predict anything they can. They'll say we can predict gravity. Wow. You really went out on a limb there predicting gravity. Okay, you have to predict something else that's measurable. Now it's interesting though, suppose I like philosophy. And so people say, well, something has to be falsifiable in order for it to be a science. I think that has sort of more in what sense. But suppose you actually have a theory where it's actually impossible to necessarily make a prediction from something. For instance, some of these they're predicting new physics on remarkably small length scales. It may be impossible to ever get to those length scales. It might be actually physical animals. But what happens if you have a theory that actually is making a prediction where it's really untestable? Is that in science? I'd actually heard this. People who I've had these debates with people who get really angry with me. Which means I want to have a more with them, but that's just me. That's just me talking. Okay, what are we talking about? Okay, we're doing this. So what happened? To the Lorentz transformation theories when V is much less than C. So let's look at my buddy gamma. So what does gamma go to?
Essentially one.
Yeah, you take any day velocity and divide it by the speed of light, that's square. That's effectively zero. What's the smallest gamma can be?
I mean, this
What's the smallest this can be?
we don't know. I mean,
Yeah, we do.
Minus infinity.
One over.
It's one, right? If your velocity is zero here, that's going to make the denominator as big as possible.
Oh,
Okay, and so the smallest value of this can be is going to be one. Okay, so in non-relativistic physics, you're going to see what. So what happens here? So we get x prime equals this gamma x minus vt. This is really going to go to x prime equals x minus vt. Okay, y prime stays y prime equals y, that stays the same. Now what does your t prime go to? T prime is this. Okay, your gamma goes to 1. I'm going to take the velocity of an object divided by c squared. What does that go to? 0. Then go to 0. So this gives me t equals t. These are actually given a name. These are the Galilean transformation equations. And it makes perfect sense. Let's figure it out. Here's this is at t5 equals t equals 0. The two frames coincide. Those two frames coincide. Now what's going to happen? So at sometime t not equal to 0, t prime not equal to 0. Right, so this is y x y prime x prime. Okay. What is this distance right here? Remember, in this frame here, we know that t prime equals t. In the Galilean transformation, t prime equals t. Everyone's going to measure the same. What does that distance equal? The frames coincide. This says the velocity v, and this has been moving for some time, v, for some time t.
X plus VT.
Mm.
X plus VT prime.
Mm.
X plus V prime.
Just this distance here. But this is moving with a velocity v for a time t. That has to be
ET.
vt.
Hmm.
Now, if I have an object here, this is x. This is x prime, so what do we have? We have dt plus x prime equals x. Your x prime equals x minus vt. Okay. And then what would you do? If I wanted the velocity, I take dx prime equals dx minus v dt. I divide both sides by dt prime. Well, in the Gaussian transformation, what do you know about t and t prime? They're the same. So that reduces to this, which is this guy. What is this? This is nothing but x dot prime equals x dot minus v. And you can go through almost all your life using this equation and be perfectly, have it work perfectly. Now, where does it fall apart?
When we start to become the
You know, when v starts getting close to the speed of light, this completely breaks apart. And what's a classic case of this? You have this. And if I'm here, if I have a laser like this, this is S prime, this is V. What would this person say? This would say the speed of light of the prime frame is what? It's going to be C. And that's V. So what would this say? If these equations are right, this person should measure speed of light being something different. And that makes sense, right? That this is let's say this is like a sound wave. So something kind of still. If you're moving this way from it, you're gonna see that sound wave actually not moving as fast because you're basically. That makes sense? And again, everyone knew that this had to be physics. What happens here, what Einstein realized is that his genius was really to take the Michelson-Morley experiment serious. He did that serious. What happens here is that this equation here falls apart. Is that this dt prime and this dt, these are not the same. Okay. And what I want to do tomorrow, I want to show you how we can take the Lorentz transformation equations and write them as the rotation matrix. And so what we're going to have is actually we're going to have now 4 vectors. So they're going to look almost normal with the exception of a little twist. Okay. So I want to show you how we can actually write these as a 4 we can have a vector like this. We have this being CT, this is going to be X, and this is going to be Y, this is going to be C. It's going to be a 4-dimensional vector. Okay. You're going to have to look at the length of this though. And I'm going to do this historically. When I do it historically, something weird's going to happen. It turns out we're going to put an I here. And the I is going to be Minkowski notation. If you tell anyone I've taught you Minkowski notation, they'll think you've been taught by an idiot. That's true. But there's a reason I want you to know that. Is no one uses Minkowski notation today. But if you want to read a lot of old books, especially a lot of old quantum books, which are very well written on many of them, unless you're familiar with that, you can't read. Because they will almost all use Minkowski notation, even though no one uses it today. We will find out why. But historically, I'm going to put the I in there, and then we'll get the I out of it. Okay, have a good day.